When we are using a graph to help us solve problems, whether they're equations or whether they are inequalities, first few things we need to locate are the boundary points, or where they intersect each other. This very first problem now, we are wondering when the two equations are equal to each other. So we graph them both. We graph the left-hand side, and I can tell that on the graph for a couple of reasons. First of all, it has a y-intercept here of -5. And it has a stretch factor of 2, so it goes up much faster than the other one. So that's how I can tell that the first equation that's written is the red graph. The second one then, y-intercept of 3, and then an a value or a stretch factor of 1 means it does not open quite as quickly. That is then the blue graph. So now I want to know with this one variable equation, because there's just x's, so it's a one variable equation, where they are equal. So they intersect right here, that is an x value of -4, and they intersect right here, that is an x value of +2. Since it is a one variable equation, my answer to A then is x equals -4 and +2. Problem B then is a little bit different, because now we have a system of equations. We have two equations, and we also have two variables. We have x's, and we also have y's. That changes our answer for this problem, because now with two variables, we actually want the coordinate point itself. So this coordinate point right here, yes, it has an x value of 4, but since we have a y value, we also want that y value. So then we have the coordinate point -4, 7. And we also have this coordinate point up here, which again, the x value is 2. But now the y value is 13. So the solution to problem B are now coordinate points. So that's what problem C here is getting after. Difference about the last two problems and their solutions: one variable equation, two variable system of equations. If there's more than one variable, we want to have our answer demonstrate that. Then we need to look at problem D, E, and F. So when we're dealing with problem D, again, I'm going to be interested in the intersection, because that is our boundary point. So now when I look at this first problem, when is the red graph greater than the blue graph? So for what x values is the red graph greater than the blue graph? So again, I know that right here and right here, they are equal. So on my number line, I'm going to represent this on a number line. My boundary points are at -4 and +2. Because it is a greater than symbol and not greater than or equal to, I'm going to have open circles on both of those boundary points. Then, for what x values here is the red graph greater? So for every x value going this way and going this way, you can see the red graph is above or has a greater output than the blue graph. Whereas in between those, the blue graph has a higher output than all of the red one. So my answer to problem D is represented here. Writing this algebraically then is going to be what's called an OR inequality. We have x is less than -4, or x is greater than 2, because my solutions are here or they're over here. So now with that same idea, if we take a look at problem E, again, I have my boundary points at -4 and 2. But now it's a closed circle because it's less than or equal to, and I want to actually include my boundary points in my answer. So my boundary points are now included in my answer. So now when is this red graph less than or equal to the blue graph? So now, if you look at between here, for all these x values, between, the red is below, or the outputs of the red are below the outputs of the blue. So I am going to then shade in between here. Writing my answer algebraically then is going to be -4 is less than or equal to x, which is less than or equal to 2, because my x value can be anywhere between. Problem F then is now a system of inequalities. Notice that there are x's and y's in both of these, compared to these two when there was just one variable. Since there are x's and y's, just like in the problem up top where I needed coordinate points as my solution, I'm now going to have coordinate points as my solution here. So I want every point that is both less than the red and less than the blue. So everything that's less than the red would be all of this over here. And everything that's less than the blue would only be these here, but then it would include all that, all this. But now if it's a system, I want only the parts that are overlapping each other. So less than both of them would be up to this line here, and then down below this one, and then again below just this blue one. So all of this here would need to be shaded for that. Again, the difference between the previous problems is now we are shading a graph, whereas the last two we shaded a number line. The very last thing is if we were looking at problem H, how does this equation right here help us solve those problems? Well, if you got everything over to one side, if I moved it all that over to the other side, I would have x squared plus 2x minus 8 equals 0. And now my x-intercept is going to be my boundary points. And again, the x-intercepts then should be 4 and 2, or -4 and 2.